this down. All right, lesson 4, types of substances and their properties. Oh, hang on. I forgot to click. Okay. All right, so types of substances. The first one we'll discuss are metallic substances and their various properties. Metallic elements generally exist at a solid at room temperature, with the exception of mercury, which is our only liquid metallic element. Metallic substances have very high melting points. They are usually hard solids. They tend to be insoluble in water, and they are good conductors of both heat and electricity. Oh, sorry, did y'all have that? Ionic substances and their properties. These are crystalline compounds that are formed when we have repeated patterns of positives and negative ions. Binary ionic compounds are formed when a metal and a non-metal combine. Sometimes it's a metal and a polyatomic ion. Yeah. And a polyatomic ion is defined as a group of covalently bonded atoms that have an overall charge. When they covalently bond, they have either an excess or a deficiency of electrons. Most of the time, it's an excess. We're actually going to look at how to write those and figure that out. Okay. Ionic substances also demonstrate very high melting points. They are all either a crystalline or a powdery solid. Most of these are going to be soluble in water. And if you dissolve them in water, they tend to be very good conductors of electricity. So the aqueous dissolved in water. They are good electrolytes. That means they conduct electricity well because they produce mobile ions when we melt or dissolve them. And if you have those positives and negatives, an electric current is able to pass between them. Molecular substances and their properties. Molecular substances are the ones that are covalently bonded and they contain molecules. A molecule is defined as a distinct unit of a molecular substance that can exist alone. You can have a singular carbon dioxide molecule or a singular water molecule. These tend to have lower melting points. They're generally poor conductors of electricity. And in their natural state, they usually are very soft and brittle. If they're solids. Okay, am I good? All right, nonpolar substances have symmetrical molecules. So we talked about that there were types of covalent bonds, and we had both polar and nonpolar. One of the ways you can determine if it is going to be a nonpolar or polar substance is by looking at how it is arranged, when how the molecule is put together. If it is symmetrical, it's going to be nonpolar. That means you could fold it in half and it would be the same. We're looking for symmetry. A good example of that is carbon dioxide, which is on the left side there, and then methane, which is on the right. These are symmetrical. They also tend to have an even charge distribution, which just means that their electronegativity values are very close to one another. And because of that, they don't demonstrate an excessive pull for the electrons. Polar substances are going to have asymmetrical molecules. And because they're asymmetrical and because of electronegativity value differences, the more electronegative atom is going to pull more of the negative charges or the negative electrons towards it. When it does that, it creates what we call a pole, where actually they get referred to as dipoles. If you look at these polar examples here, like hydrochloric acid, you will see this little symbol here. This is a lowercase sigma in the Greek alphabet. And it's a plus sign. And then here we have one with a negative, indicating that although this is an electrically neutral molecule, if we were going to look at it from an overall standpoint, if we were to examine it closely, we would notice that there's a little bit more of a positive charge on the hydrogen side and a little bit more on the negative. These are partial positives and partial negatives. And this is going to, we're talking about intramolecular bonding. And when we start talking about intermolecular bonding, these dipoles play a role in allowing molecular substances to stick together. Specifically, if we were to have water, if we have partial positives and partial negatives, well, the rule of attraction still applies. So these partial positives will be attracted to the partial negatives of other water molecules, creating hydrogen bonds. It's also when we think about being able to dissolve something. If we want to dissolve it, that means we need to take it apart. And if we're going to take it apart, we need to have some attractive forces generally for that to take place. If I put HCl in water, because it has a partial negative, it's going to be attracted to the partial positives of the hydrogen molecules in the water, and then the negative oxygens. And so it's going to provide force that pulls it apart and makes it dissociate. But as far as just if you were to go through a list, a picture of these things, if you have symmetry, you're looking at a non-polar molecule. If you are asymmetrical, you're going to be looking at polar molecules. Those are just not the same. And so here, if there was another hydrogen on this side, okay, it'd be symmetrical. Here, you can see that this is bent. It doesn't have, it would have to have a hydrogen coming out here and a hydrogen coming out there in order for it to be symmetrical. Same thing here. There's only 3 hydrogens, and they're pulling at different rates. I didn't realize I had that sentence on here. Called dipoles because there are 2 poles. There's a positive pole and a negative pole. A pole, of course, refers to an attractive force. So we have a north pole and a south pole, but basically those where magnetic fields focus. You don't have to write this down, but you'll probably need to reference it at some point, especially when we do the practice for this section. There are several molecular shapes. We have linear, which of course makes sense, it's in a line. Then we have nonlinear or bent. Water molecules are bent molecules. Trigonal planar, pyramidal, tetrahedral, square planar, trigonal bipyramidal, octahedral. These are just a sampling. There's really 5 main shapes that we work with this particular author of the resources that I use for this course. And so not all of these will be something that we're, having to freak out about. You can determine the degree of the bond and the molecular polarity based on electronegativity values. If you are to determine the electrical charges between the atoms, you can then figure out if it's going to be symmetrical or not based on its electronegativity difference. And I've put a chart down here at the bottom of this, and I would jot that down, this information. It goes from 0 to 4 total, and from 1.7 to 4.0 is an ionic bond, and from 0 to 0.4 is nonpolar, 0.4 to 0.7 or 1.7 is polar. So if you can determine the electronegativities of the two atoms involved in the bond, you'll calculate the difference between those and then apply it to this chart, and you can determine what type of bond you're going to have. If you do that and you know it's going to be a polar molecule, then you realize when writing out a structural formula for this that it's going to be an asymmetrical structure. So that's just another way to get those correct. Here it is, just larger scale. Sorry. I forgot I put that in there, so it'd be a little bigger, just in case you needed to see it a little bigger there. Yes. That's a metallic bond. That's not going to be ionic or covalent. No, it's a metallic. No. I mean, they do have electronegativities, but we only apply them when they're in a ionic bond. I guess, I mean, you could, if you were going to have to put it that way, but I mean, it just copper, it's just a whole bunch of copper atoms. So the electronegativity doesn't matter. They're all the same atom. Does that make sense? It's just copper bonded to coppers, like hundreds of them, like in a sheet. So that's all that exists there. So it doesn't really matter about the electronegativity difference because copper is the only thing present in that metallic bond. But if we were to take copper and bond it with oxygen, that becomes an ionic bond because we have a metal and a non-metal. And so we would look at its electronegativity value. I think that's it. Yep. All right, so let's practice. And then we'll do lesson 5.